right, good morning. And today, homework number 7 is due, so I think a lot of you have already put it up there, but either put it up there right now or at the end of class. The next homework assignment over Chapter 8 is due a week from today. And we'll be discussing some of that today and some of it about Monday. We will be talking really about Chapter 8 on biomagnetism today, and we'll continue on the part on magnetic stimulation of the brain on Monday. And then we'll move on, skipping Chapter 9, move on to Chapter 10 next week. So, when I was in graduate school, one of the first things that I was assigned to do as a young graduate student was to measure the magnetic field of a single nerve axon. So nerves produce their own magnetic fields. They have currents, and currents produce magnetic fields. So one of the first things we're going to do today is we're going to go through and see how you can calculate what the magnetic field is from either a nerve axon or a strand of cardiac muscle or whatever you want to look at. So you probably, hopefully you remember from your introductory physics days that there's really two ways you can calculate magnetic fields. They're equivalent, but they are kind of different methods. One is Ampere's law, and the other is the law of Biot-Savart. So we're going to analyze the magnetic field produced by an axon, first using Ampere's law, and then we'll go and do it using the law of Biot-Savart, and we'll end up getting the same result in both cases. So what I did in graduate school is we dissected out a single axon, didn't use a squid, used a crayfish, which has a few very large axons down its tail, and put it in a dish, threaded it through a little toroid, and measured the magnetic field as it propagated by. So let us see how we would analyze that. Okay, first of all, Ampere's law. Ampere's law is going to look a little complicated, but in fact we're not going to be using it in any complicated cases. It says the integral B dot dl around some closed path is equal to mu naught, a constant, times the current enclosed in that path. So here's our nerve axon, and remember, magnetic fields are produced by the right-hand rule. If you have current going down the axon, you have a magnetic field wrapping around it. So since this is the current, the magnetic field is going to come around like this, according to the right-hand rule. And the question is, how does it fall off with distance, and how do we calculate that? If you just had a wire, think of this for a moment as just as a long, straight wire, you can use Ampere's law. Ampere's law says you have to integrate B times dl. But if this is just a loop around the wire, that means the magnitude of the magnetic field is uniform. And all you really have to do is multiply magnitude times the circumference, the path length around the loop. So if we go around this loop, we get that that's just B, and this is going to be a radius r out here. It would be 2 pi r is the distance around, is equal to mu naught over I enclosed. Or in other words, B is equal to mu naught I enclosed over 2 pi r. This is kind of the famous equation for the magnetic field of a wire. Now, why is it more complicated? Well, before we talk about that, let's just mention a few things. Mu naught, that's a constant. That's a basic constant from magnetism. It's equal to 4 pi times 10 to the minus 7 Tesla meter over amp. And you might ask, why is it a strange constant that has a 4 pi in it? And that's because it's defined in this way so that the speed of light comes out to be a particularly special value. So just take it as a constant of nature. What's a Tesla? That's how you measure the units of magnetic field. So a 1 Tesla magnetic field is a big magnetic field. That's like what you have in a magnetic resonance imaging machine or inside a piece of ferromagnetic material. Earth's magnetic field is about 0.0002 Tesla. It's about a fraction of a millitesla. And that's still big enough to measure with a compass. We're going to find these are going to be much smaller magnetic fields. Biomagnetism deals with really small magnetic fields that are small enough that they have almost no biological effect in themselves, but they are big enough to measure if you have really sensitive instruments. So let's look now at a nerve axon. It's going to have current going down it, like we did here. I'll call that I0. But it's not going to extend all the way down the axon. Remember, it's going to only be present when you have voltage gradients. So we'll assume this is more like cardiac tissue in that it has a resting out here and is during the plateau phase over here. So you just have currents where there's the upstroke of the action potential. Now, we studied how the continuity law says if the current ends, there's no current down here, it's got to come out of the axon, and over here it's got to be going into the axon. And it also forms closed loops. There's salt water out here. The conductivity sigma E. That's the whole point of the experiment was you take the nerve and you put it in a dish surrounded by saline. So you get currents that flow out here, and that produces electrical potentials or voltages out there, and that's what we discussed. And now we want to calculate the magnetic field. Let's see if I can get a different color here. Use magnetic fields in orange. The magnetic field is going to be coming around like this. And we know from Ampere's law, the magnetic field depends on the current enclosed. That's the current enclosed in this loop. For the straight wire, there is only one current. For the nerve, there's two. You have the current inside the axon, and then you have some of this extracellular currents going through this loop of radius r. So to get the entire enclosed current, you really have to calculate what fraction of this extracellular current passes in this loop. And you see the amount that passes in the loop will depend on the radius that you're looking at. So if you imagine this is being recorded by some little recording device, it's like a little donut that's threaded around the nerve. It's how much current passes through the donut. They call it, this is the intracellular current, and this is called the return current, the amount of the part of the extracellular current that comes back through. So B is equal to same calculation as before, except now this is the inside current plus the return current. Usually the return current will come out and be negative, so this will be subtracting off, and you'll have a smaller current because of this return current. If you tried to do this experiment in air, so there's only a thin layer of moisture on the outside, all of the current would be forced to go back through the extracellular space. You have current going down, coming back, and you'd have no magnetic field. So it's important that the thing is lying and sailing. So we have to calculate this return current, and that means we have to know something about the extracellular potential and the extracellular current distribution outside the cell. Okay, well, we calculated the extracellular potential in this situation, and it was either in one of your homework problems or in class. So how did we do it? The extracellular potential. See, the step in general, let me just outline the calculation. To get the return current, first we're going to get the extracellular potential. Then we're going to differentiate it to get the extracellular electric field. Then we're going to multiply by the conductivity to get the extracellular current density. And then we're going to integrate that current density to get the total current going through the this path, or the enclosed in the path. So those are the three steps. So the first one is the extracellular potential. All right, so we did this before. We said that if there's a current going down, all of the current comes out here and goes back in here. So it had a 4 pi sigma E. Now, suppose we're out here at some spot xy. And we have to find, basically now, we have to divide by 1 over r, because you get a 1 over r in the calculation for the potential. We need to find what this value of r is. So what's that going to be? We have 1 over, basically how big is this r? You divide it into two pieces. This side's y, is the x direction. Here we're going to take x equals to 0 here. We're going to call this x equals to b and x equals to minus b. So that kind of shows you where we are along the axon. And this distance here, this is at position x. So if you look at this triangle, how long is side capital R? What would that be in terms of x and y? Give me some help here.
A squared plus y squared. Square root of b squared.
Okay, it's going to be square root of certainly a y squared from this side. Now, the trick is this length is a little bit trickier. It's got a b in it, but it's actually x minus b is going to be what that side is. So you get x minus b squared. All right, and we also have another source over here. It's going into the axon, so it's negative, and it's going to have its own triangle, and its side here is now going to be x all the way to 0 plus a little distance b. So y squared plus x plus b squared square root. And that is the extracellular potential. It's basically straight out of chapter 7. Okay. Now, we know VE is a function of x and y. So let me point out here. How do we find the electric field? In particular, I want the electric field along the x direction. How's that related to the extracellular potential? Anybody remember the relationship between electric field and potential?
Negative sigma times the derivative of the voltage.
Right, except that the sigma would be if you're doing current density, but if you're just getting electric field, it's just negative the derivative of the voltage. And since we want the electric field in the x direction, we take the derivative with respect to x. So now we're going to try to find the electric field. And that has the minus sign, has these constants out here. Now we have to take the derivative of this with respect to x. So this is really y squared plus x minus b squared all to the minus 1/2. So what's the derivative? Lily, what's the derivative with respect to x? Anybody can chime in.
You just want the final thing, or
I want
breakdown?
I want this piece, this term here. What's the derivative of this term with respect to x? Yeah.
X minus b over.
Okay. You're doing a little bit. This is the part you get from the chain rule over what?
Over x minus b all squared.
Over x minus b all squared.
Yeah,
I'm going to put that over on this side since I've written it.
Plus y squared.
Y squared.
Everything to the 3 over 2.
3 halves. So let's see how we got that. This is all to the minus 1/2, so you get a minus 1/2, and then you get this whole thing to the minus 3 halves, and then you'd have from the chain rule the derivative to the inside, which would give you a 2, which is going to cancel that 1/2, and it would give you x minus b. There's a minus sign, I think, that's still floating around in here that needs to be in there. Eventually, it'll probably cancel this minus sign, but I think when you actually do it at this point, you'd have a minus 1/2, and then you'd have this. And now for this one, you're going to get the same thing, except now you have an extra minus sign, so it'll be plus, and now you have x plus b, and you have y squared plus x plus b squared to the 3 halves. So there you have it. Okay, now I'm going to do some, running a little low on chalk space, so I'm going to do a little eraser math. Hopefully you don't mind. If you want the current density is just the conductivity times the electric field. So the current density becomes, multiply this by the conductivity, but I already have a conductivity down there. So that'll cancel this conductivity, and that's just the current density. Okay, so we're making good progress. Now, I'm going to make this problem a little bit simpler. I'm going to say I don't want to know the magnetic field anywhere. Right now I have the magnetic field at any position x, y. I just want to find the magnetic field right here at the center at x equals to 0. Because that's where it's going to be largest. So let's see, if we want the magnetic field at x equals to 0, well, first of all, we can get the current density at x equals to 0. So Jx, x equals to 0. Okay, so here we have x equals to 0. You just get a b up here. Here you get a minus b, but there's another minus sign here. So you get b and you get b, so you're going to really get two b's. Here, when you have x equals to 0, you get y squared plus b squared to the 3/2 in both terms. So you get a minus I0 over 4 pi, and you get a b, you get a 2b, because there's two terms, and you get y squared plus b squared to the 3/2. And again, I'm going to do a little eraser math here. That becomes 2, and that goes away because it was 2 over 4. So that's and that now is your current density. Okay, good. Got a minus sign, but we expected that because this current density is going over to the negative direction. How do we say we're going to get the total return current? What are we going to do? You have the current density throughout the extracellular space. We're really going to integrate that over this whole area inside this loop. It's an Amperian loop. You have this path, which is the circle around here, and you have the I enclosed by that path is what's in Ampere's law. So, the I enclosed, well, that's equal to, first of all, the current inside the axon is all enclosed. That goes through the loop. Then there's this fraction of the extracellular current. So you're going to get plus, and you're going to get this thing, integral Jx over the area. This is this area inside the loop. So we've got to do this area integral. All right, so let us do the area integral. If we look at this from inside on, we are integrating essentially over this loop. So we're going to divide it into a bunch of little discs here. Since the radius out here, total radius is called r, I'm going to call the little radius that we're going to integrate over y, and this is going to be dy. So what's the area of that shaded area there?
2 pi r dy.
That's right, and 2 pi. It's I naught plus, and this is going to have the dA becomes 2 pi y dy, because it's just the area out to y. And you're going to integrate over y. How far you integrate over y? From 0 on up to r. So, and that's jx, which is this thing. So there's a minus sign in the jx, so you get a minus I naught over 2 pi, and then you're going to have integral of b over y squared plus b squared to the 3/2, and then you have your dA 2 pi y dy. Making good progress. 2 pi's cancel. The b will come out of the integral. But we're still left with this integral y dy over y squared plus b squared to the 3/2. So, we need to know how to do that. So, quick. Carolyn, what is the integral? Anybody know that integral? Well, I wouldn't have known it either. It is something that I just look up in the integral table. So I did. So the integral of, I'll call it z just to make it general, z squared plus b squared in general to the 3/2 is minus 1 over z squared plus b squared square root. You probably do it by some trig substitution or some kind of funny substitution, but we don't need to know how to do the integral. We're just going to use that. So, I0 is in both terms. Here you've got a 1. Here you've got a minus. This has a b. And then here's this integral. So you're going to get a minus sign here, which is going to make that a plus. And you're going to get a 1 over y squared plus b squared square root. And you evaluate this at 0 and r. We're almost there. Let's just evaluate it at the two endpoints. When y is equal to r, you get plus b over r squared plus b squared square root. The lower integral, you set y equal to 0, and that just gives you a b downstairs, which cancels that b. It's a lower integral, so it's minus b over b, which is 1. So once again, these cancel. So I enclosed is equal to I naught b over r squared plus b squared square root. And therefore, the magnetic field is mu naught I naught b over 2 pi and r times r squared plus b squared. That's I0. That's a b. And there we have it, the magnetic field outside this axon. Now, what's our usual theme? Our usual theme is that if we calculate, first we started with a physics problem. We did a bunch of math and we got a final expression. Now we want to go back and analyze that and try to see if we can understand what's going on with the physics again. So I'm going to need more space. I'm going to have to erase some of this. If people have any questions before I do any erasing. Okay. I'm going to start erasing from this side. And get this. And get all that. That should give us enough to do this analysis. What happens if R is a lot less than B? So in that case, let me draw it up here. You have a nerve. And you have a current going down the nerve. This is B and this is minus B for X. It comes out and you're measuring a magnetic field real close because R, the distance out, is very small. So you have this case. What does our expression become if R is really small compared to B? Let's take the limit with R small. What do you get?
That expression is just going to be b, because r squared plus b squared is going to equal b squared.
That's just going to be b squared under the square root, so it's going to be b. It's going to cancel that b. And all you have left is mu naught I over 2 pi r, which is exactly what we had for a straight wire. So if you're really close, the return current all passes out here, outside this path, and the return current doesn't contribute anything, and it's just the current in the axon, and you got a long straight wire. Makes sense. It almost had to be that way. How about if R is much greater than B? So now you have your axon, and you have a current that's over just a small path along here. So here's B and minus B, and it comes out, and then you have your current spreading out like this, and your point where you're measuring the magnetic field is way out here, a long distance away. So a lot of the current comes back through. And so your R is out a large distance compared to B. What does this equation become when R is really big?
mu naught IB over 2 pi r squared.
IB over, okay, when R is big, this is big compared to B, so it just becomes R, and there's another R, so you get 2 pi r squared. It falls off, not as the first power, but the second power. It's a dipole field, basically. You could call, sometimes people write this as mu naught times 2IB over 4 pi r squared. And now this thing, 2IB, is really the current, the dipole moment. It's the current times the length. The length of this whole thing is 2B. So this could be thought of as a dipole moment, mu naught, and then you get the 1 over r squared fall off. So, just as we saw dipoles and dipole electrical potentials, we also get dipole magnetic fields, mu naught P over 4 pi r squared, where P is just the dipole moment. Depends on the current. This is I sub 0. Falls off r squared, falls off much faster. The reason is, as you go out farther, you lose in factor of r here, but you also get more and more of the return current going through, the extracellular current going through the path, so you get more and more return current, and those two factors combined to give you the 1 over r squared fall off. And that is how you can calculate the magnetic field. So what we did is, we did this experiment. I wanted to show you a couple things. First of all, is this. This is actually a picture of a nerve axon and its extracellular currents. Now, technically, a nerve axon would have a dipole here and another dipole following behind. So this is really it's really propagating in this direction. This is the front dipole and the back dipole. This is the axon, and this is the extracellular currents. By the way, this was when I graduated from graduate school. My PhD advisor's name is John Wixwell. He's also a machinist. He made this thing for me. It's my going away present of the magnetic field. Now, we took a little ferrite core donut and we threaded the nerve through it. And on the donut was wrapped a bunch of wires. So it acted like a little pickup coil. And as the magnetic field passed through, the magnetic field increased and then decreased and then went back to 0. Changing magnetic field induces a voltage in the wire of this around this donut, and we're able to measure this response from the magnetic field. So this is kind of a intuitive picture of what's happening. And the other thing is I worked so hard to get that data. I put it in a picture and I've kept it in my office. This is the magnetic field of a nerve axon. There's the upstroke magnetic field, and then there's the repolarization signal as it propagates by. That's for the noise is just because this is a really small magnetic field. In fact, how small is it? It's on the order of 1/10 of a nanotesla. Nano is 10 to the minus 9. So 1/10 of a nanotesla is a really small field. One reason why, it's much smaller than the Earth's field. So why can you even measure it? Well, the Earth's field's static, so it's not going to be picked up by a stationary pickup coil, which is relying on Faraday induction. It has to have some kind of changing magnetic field. So we get rid of the Earth's magnetic field that way, and we can record the changing magnetic field and get the pickup coil. So it worked. Originally, we were going to do the experiments on lobsters, which have even bigger nerve axons. But I got there, and I had to learn how to do the dissection of the nerve, and it's a little expensive on lobsters. So Wixwell told me to practice on crayfish until I got good enough, and then we'd switch over to lobsters. Well, I got so good on the crayfish that we never had to switch over to lobsters, so we didn't get the nice lobster dinners, but we got the data from the crayfish. Okay. One of your homework problems, I believe, let me just check and make sure. Chapter 8, number 32. No, that's a different problem. Well, okay, I don't know if this is actually on your homework problem, but suppose Here's what happened one day in the lab. I'm doing this experiment. Remember, this whole thing's underwater. Got this toroid around the nerve. So for some reason, I lowered the level of the water or something, and a bubble got trapped between the inside of the toroid and the nerve. So it's in this region right in here, blocking the whole space there. What's going to happen to the magnetic field? What's going to happen to the magnetic field if a bubble gets trapped in there? Well, the magnetic field has two parts. Intracellular plus a fraction of the extracellular cancels it out. If you block that extracellular current, you're seeing just the intracellular without that part of the extracellular that cancels it. So the magnetic field went up. So I'm sitting here doing this experiment, and this bubble got trapped in there. So I said, hey, this is kind of interesting. So I repeated the experiment with the bubble in there. Magnetic field went up, and then I poked the bubble out, and the magnetic field came back down, just showing that you could, it really shows that this return current makes a difference in the calculation. So sometimes things happen by accident, and it's kind of useful. Okay, now we're going to do the whole problem again. We're going to do it a different way, using the law of Biot-Savart. And the only reason I do this, you're not going to have to do law of Biot-Savart on an exam. You might have to do Ampere's law. That's fair game. Law of Biot-Savart is not going to be on the exam, but one of your homework problems has the law of Biot-Savart. So you're going to have to do it at least for the homework problems. So that's why we're going to do this whole calculation again using a different method. So here we go. I'm going to leave this result. And this was Ampere's law result. Now, Biot-Savart law says the magnetic field is equal to mu naught I0 over 4 pi, and you integrate around the path that the current's flowing, and that's ds, that's the path along where the current flows, cross r over r cubed. R is the distance. So suppose you had a current going down a wire like this, and you're measuring the magnetic field here. You'd integrate over this current, and this would be a little element of ds, and this would be r, the distance to the magnetic field. Now, the reason magnetism's harder than electricity is because you have this crazy cross product in it. That's all wrapped up. That's all really equivalent to saying you have the right-hand rule or the funny direction. So we need to define what these are here. We're going to have, this is almost our nerve axon. Our nerve axon, you had the current that extends from x equals minus b to x equals to b. So there's a current flowing along here, I0, and we're only going to consider the intracellular current now. We're going to integrate over it. ds. Well, that's just going to be in the I hat direction. Another complication for Biot-Savart law is it's all in vectors. But this is the x direction, so that's the I hat unit vector, and so it's just dx in the x direction. That's all ds is, because we're going to integrate over that current. R is a little more complicated, because you're out here at some position, and this position is going to be x, y. So R is really, it's going to be x, x minus b I hat plus y j hat. Okay, I think this is correct. Now, we need the cross product. We need ds cross r. So when you're doing your problem in the homework, you're going to have to calculate this cross product. The way to do cross products is to use this little determinate memory device. There's ijk, then there's ds. ds has dx, and there's no j or k, so 0, 0. And r is x minus b, y, and 0. And what this really means is it means I hat times this subdeterminant, but that's got all zeros, plus j hat times this subdeterminant, really minus j hat times this subdeterminant, but again, zeros. But you get a k hat times this minus this times that. Well, that's a 0. So all you really get is y dx. So this thing gives you k hat y dx for the integral you're going to have to do. Notice that makes sense. This is at point y, so that's the y direction, and I across the right-hand rule, you expect the magnetic field to be coming out of the board in the z direction. Okay, so we're almost there. We got b is mu naught I naught over 4 pi, and now we're going to integrate. There's a k hat that comes out of the integral, and the y, in fact, comes out of the integral. But you're going to get minus b to b of dx over, and what's the magnitude of r? You're going to get r minus b squared plus y squared square root. And we want to evaluate this just like last time. We want to evaluate it at the center. So we'll set x equals to 0. So b at x equals to 0 is going to be mu naught I naught over 4 pi in the k hat direction. And now the b goes away, or the x goes away, and it's just b squared. Integral minus b to b of dx b squared plus y squared. That's what you get when you evaluate it, x equals to 0. So again, quick, what's this integral? It's a different integral than last time. Who knows? Let's just look it up in the integral table. So I looked up in the integral table. dz over z squared plus b squared square root is z over b squared z squared plus b squared. That is from the integral table. So I'll just use that. Mu naught I over 4 pi k hat. So now the integral has z there is x here, so you get an x over b is like this. I'm okay. Actually, I've done something wrong here because I don't set x equals to 0. What I want to do is I want to find integrating over x. Oh, blast. Integrating over x. Well, I'm going to have to straighten out this, and I'm not going to be able to do it right this second. But let's just take this. You end up getting something like this. You get a downstairs, you're going to get an r squared. Okay, this is not good. You're going to get b squared, and you're going to get this y. Oh, rats. Okay, embarrassing. I have kind of screwed this up. What I'm going to do is I'm going to write up the derivation and send it to everybody so you'll be able to see it. But can anybody guess what the answer is going to be? Well, the answer has to be exactly what you got from Ampere's law. And that's really, you can almost see it coming. There's the square root, there's the square root, and so it's going to end up being exactly like what you got from Ampere's law. But I have messed up the derivation for Biot-Savart, so I will send it around to everybody. Again, you won't run into Biot-Savart on the exam, but you will have this one homework problem where you're going to have to do it. Not quite sure what happened. But anyway, you can't have a different answer than Ampere's law because the magnetic field is the magnetic field. The magnetic field doesn't care how we calculate it, as long as we calculate it correctly. So you end up getting the same result. So I'm sorry, I will fix that and send it around. Okay. And the fact that Ampere's law and Biot-Savart law actually match was not obvious in the calculation. I did a somewhat more complicated calculation in graduate school, and it wasn't obvious that the two were matching until I finally figured out this weirdo mathematical way to show that the two have to be the same. All right, so let's talk a little bit about the homework. Homework problems. So, let me get the evidence here that I screwed up. I should have turned off that stupid video camera. No, it's going to give me evidence forever. Okay. Problem 10 in the homework. This is the problem where you need to use the Biot-Savart law. So let me just sort of outline it, and hopefully I'll do this one right. Here's your x, y, z coordinate system. Okay, so x or y, z, kind of drawn in perspective. You have this circular wire here like this, and it's of radius a, and you have current flowing around it, I. So it's going to make a magnetic field. And what you want to do is find the magnetic field at some point along the z-axis. Find what the magnetic field is. I mean, really the magnetic field is going to be going like this everywhere, but all we really care about is what it is along this axis. So you're finding magnetic field B. So what we need to do now is we need to set this up so we can do law of Biot-Savart. So the law of Biot-Savart, first of all, we need to integrate around this loop. So we have a little ds, which is really going to be, that's a d theta. And it's going to be in the theta hat direction if we use polar coordinates. It's going to be going around the loop around the theta direction. So one thing that's not given in the problem is the relation between x, y, z, and r theta, really the polar coordinate relationships. So I'm going to give those to you so you'll have them. So this is probably going to be needed in the calculation. Theta hat is minus sine theta I hat plus cosine theta j hat, and r hat is cosine theta I hat plus sine theta j hat, where this angle here is theta, and r would be, in this case, a, the distance out. So that's the relationship of theta hat and r hat. So you can say that ds is equal to a times d theta times theta hat. So that's minus sine theta I hat plus cosine theta j hat. You also need r. R is basically this vector here. Let's see if we can figure out what r is. Well, r is going to have two pieces. It's going to have part in the z direction. So really you can think of it as a vector here and a vector up to here. It's going to have part of it in the z direction, and that's just going to be z times k hat. The bigger z is, up, the larger r. And it's also going to have this piece, it's minus because it goes into the origin, a times r hat. R hat's just, again, the polar coordinates, which is z k hat minus a cosine theta I hat plus sine theta j hat. You're almost there. Now what you need to do is law of Biot-Savart has ds cross r. So I'm going to let you do it. Let me just write it down. Remember how you do a cross product. I, J, K, S, ds is going to be AD theta times minus AD theta sine theta. J hat is plus cosine. It's AD theta cosine theta. And there's no K hat. R is I hat has a minus A cosine theta. J hat has a minus A sine theta. And Z for K. Now, you do a cross product. You take I hat is this times this minus that times that. That's 0. So I hat has a Z, A, D theta, cosine theta. J hat is minus this times this minus that times that. K hat is going to be this times this minus that times that, which is going to be kind of a complicated thing. So I'm going to let you finish this. It's a homework problem. But you put that in, that's what you need to put in to the law of Biot-Savart, and then you integrate around theta, around the whole loop. I'll give you a little hint. You just know by symmetry that the magnetic field along the center is going to be pointing straight up, which is the z direction. So it's going to turn out that the I and j hat contributions are all going to integrate out to 0. You're going to get some integral over some angles that are going to integrate to 0. The only thing that's not going to integrate to 0 is going to be these. You can see that happening because this is going to have a cosine. Integrate the cosine over from 0 to 2 pi. It's 0. Integrate the j hat term is going to have a sine. But the k hat term is going to have a sine squared. That's going to give you some integral, cosine squared. So you're going to get something a little more complicated. Really, I've sort of done all the difficult part for you. The integration is going to turn out to be really easy. So that's problem 10. That's the first problem in your homework. It's really the only time you're going to run into the law of Biot-Savart for the calculation. Okay. Any questions on that? Okay, I think you have to try the homework problem, but that should get you started. The next problem in the homework is problem 13. Problem 13 is almost exactly what we did earlier today. It's just got some of the notation a little bit different. You have an axon, you have a current flowing down it, but the current goes from x equals to 0 to x equals to x1 instead of minus b to b. And you're asked to calculate what's the magnetic field out here at point x0, y0. And you can either use Ampere's law or the law of Biot-Savart. I don't really care which one you use. I'm assuming most of you use Ampere's law because that's the one we had most success with together. So remember, you're going to get extracellular potential, and it's going to come out. Some of it will go inside, some won't. You can integrate over, just like we did in class, you can get an expression for the magnetic field. So the only thing that changes really is just how you label the x-axis. So I'll let you work on that because it's pretty much otherwise the same as what we did. Okay. This homework assignment might be a little bit more difficult than some of the previous ones, but not too bad. Okay. Problem 24. Have any of you ever, how many of you have ever taken a class in vector calculus? Divergence, gradients, and curls, that kind of thing? Okay. A few of you. Well, there's a way to write Ampere's law. Remember, Ampere's law, the way we wrote it, was B dot dl around the loop is mu naught times the current inside. I enclosed. But there's a way to write it, that's the integral form of Ampere's law. There's a way to write it in a differential form. And we're not going to prove this, but the differential form is curl of B is equal to mu naught current density J. This is the differential form of Ampere's law. Don't need to see the derivation. Just know this is it. Now, what we do is we say, suppose you measure the magnetic field and you want to find out what the current density is. Well, you just take the curl of the magnetic field and you divide by mu naught, and you have the current density. This is a method that's been used based on magnetic resonance imaging. Magnetic resonance imaging can be used to measure the magnetic field. Then if you take the curl, you figure out what the current density is in the tissue. So it works. So all you got to know is how to calculate a curl. Here's what I'll give you a hint. Curl is like the gradient crossed into B. So you do that same thing with the determinant, except now this vector is d dx, d dy, d dz. And then you have B, dx, dy, dz. So that's the little simple way to remember what the curl is. If you want to write it out in detail, it is I hat times the lower derivative, which would be dbz dy minus dby dz, minus j hat times dbz dx minus dbx dz, and so on, and k hat. So you can get it. So now, the problem gives you bx, by, and bz as a function of position. All you got to do is take these derivatives, calculate the curl, divide by mu naught, you get the current density. So imagine you're in an experiment where you measured those. All you have to do is take the derivatives and get the current density. So that is problem 24. If you have questions, now is the time to ask. Okay, well, you'll have plenty of other times to ask, but let's do problem 25, and let me just introduce that. Okay, problem 25. I consider problem 25 to be a scavenger hunt, because you don't have to actually do any math. All you got to do is look through the textbook and find 4 equations. And the 4 equations you're asked to find is, first of all, Ampere's law. Well, Ampere's law is essentially this. Let's do it in the differential form. You get del cross B is equal to mu naught J. You just write it down. The only thing is, Ampere's law, in its most general case, has an extra term, something we usually ignore, and that is called a displacement term. So I'll let you guys go find it. It's an extra term that gets added in there. It has to do with electric fields that are changing with time. It's actually the term that Maxwell himself added in order to get electromagnetic waves out of the equations. But that's Ampere's law. Faraday's law. Faraday's law is what we're going to talk about next class. Changing magnetic field produces an electric field. So all you got to do is you can write it like this. It can be written as in terms of a curl again. You can write it in an integral or differential form. You get curl of E is equal to something. You go hunt through the book and find the equation for Faraday's law. And find out what the question mark is and write it down. Okay? Gauss's law. Gauss's law looks something like del divergence of E if you write it in its differential form. So Gauss's law. Again, look in the index of the book. Find Gauss's law. Look it up and find out what goes over on this side of the equation. One more. You can probably guess what it's going to be. Here's a divergence of E and a curl of E. You're going to have a divergence of B because you already have a curl of B. I'm going to do this one for you because that's just equal to 0. That's called Gauss's law for magnetism. You could have looked it up, but I'm not sure the book actually gave it this name, so I will give it to you. All you have to do now is look through the book, find what goes on these right-hand sides, and there you have a collection of equations. These are what's known as Maxwell's equations. All of electricity and magnetism is really described in these equations. People put these equations on t-shirts. So basically what I want you to do is to realize that we are discussing, what we're discussing here with our bioelectricity and biomagnetism is the basics of Maxwell's equations. You can solve these equations and get electromagnetic waves and predict all kinds of things. We're not going to do that. But we are going to be discussing. We discussed Ampere's law today. We're discussing Faraday's law on Monday. We discussed we didn't really do much with Gauss's law, but it was back there in equation 6 or 7. Okay. A few other things I wanted to mention. Any questions about these homework? This is some of the homework problems, probably the first 4, and sort of how to get you started on them. Okay. We're going to talk a little bit more about measuring magnetic fields. People measure magnetic. Remember how we did the electroencephalogram, the EEG. We talked about this last class. You had a person. Here's their head. And you put a bunch of electrodes on their head, and you measured the voltage difference between them. You were able to measure the electroencephalogram. Well, you can do a similar thing called the magnetoencephalogram. Here's the person's head. And what you do is inside there's a dipole that's creating this voltage. Inside here is a dipole that's creating a magnetic field that's coming around E. So you put a magnetic field detector out here outside the head, and you measure the MEG. So you put a coil of wire, basically, and you're detecting a changing magnetic field. By induction, you detect the magnetic field produced by the brain. That's the magnetoencephalogram. Now, it turns out these magnetic fields are really small. When we did our experiment, we saw 1/10 of a nanotesla, and that was right next to the nerve. If you get out a distance a long ways away, several centimeters outside the head, it gets even weaker. These magnetic fields are less than a picotesla. Pico is 10 to the minus 12. So they're really small magnetic fields. So what people usually do is they use something called a squid magnetometer. It's got absolutely nothing to do with the squid Hodgkin and Huxley used. It's a superconducting quantum interference device, magnetometer. It's usually done at low temperatures. So you got liquid helium, and you got this coil that's down inside the liquid helium, and it's got some quantum properties, and you can measure magnetic fields that are really, really small using these. So people who do the magnetoencephalogram usually have what's basically a big dewar holding liquid helium or liquid nitrogen that fits around the head. And inside the dewar are a bunch of these little coils, and they're measuring magnetic fields all around the head. And they can get data to analyze them. Now, a few properties of the magnetoencephalogram that I want to point out. Let us make a chart. EEG is kind of like what we did last class, but I want to compare EEG to MEG now. And the good things and the bad things. Okay. Now, first of all, I don't have quite enough time to prove this today, but in the magnetoencephalography, if you treat the head like a sphere, and you have a dipole that's pointing straight up like this, it's called a radial dipole, the magnetic field produced by that dipole is exactly 0. You only get a magnetic field if you have a dipole like this, tangential dipole. Then you get a magnetic field outside the head. Outside the head, the magnetic field from a radial dipole is 0. And this is kind of a problem. You can see voltages from that. The electroencephalogram gives a signal. No magnetoencephalogram. So you get a signal from a radial dipole in the EEG. But you don't get it, so I'm going to put it under bad. No signal from radial dipole in MEG. So if if you're trying to study the brain and it just so happens that you induce a dipole that happens to be radial, you're going to miss it in the MEG. That's absolutely true for a spherical head. For a head that's a little more realistic shaped, it's really suppressed, but it's not exactly zero. Okay, another thing that's kind of interesting about the brain. If you do a three-sphere model, remember our three-sphere model? We had brain, skull, scalp. If you do a three-sphere model for a magnetic field, the only ones that are non-zero are the tangential ones. Now, if you do a three-sphere model, the EG is affected by it because this is a resistor. The skull is high resistance, so it smears out the potentials, so the skull resistance has a big effect. But by almost a miracle, when you do the calculation for the magnetic field, the skull resistance plays no role. And that's good, because you don't usually know what that skull thickness and the skull resistivity are exactly. So one of the good things about the MEG is there's no effect from the skull. Again, that's exactly true for a spherical head, and it's only approximately true for a realistic shaped head. But you get a big effect from the skull for the EEG. And since you don't know really the detailed properties of the skull, this makes it hard to analyze your data. What else? Okay. The electroencephalogram, you have to attach electrodes to the scalp. It's not a big deal. It doesn't hurt. It's not all that expensive. But, you know, if you had, say, a burn victim who had part of their scalps burned, you can't attach electrodes. There are situations where it's hard to attach electrodes. If you had somebody with a whole bunch of hair, you might have to shave their head in order to do it. So it's kind of bad, not a big deal, but it's bad that you must attach electrodes to measure the EEG. It's just very slightly inconvenient. Whereas the magnetoencephalogram, you just take this big dewar full of these coils and you just set it on next to the head. Usually it's shaped like a helmet, so it's like putting a football helmet on. And there's absolutely no contact with the head. So, good thing about MEG is it's completely non-contact. That might be good if you're dealing with little kids who might get all nervous putting electrodes on them, or just sitting there with the helmet nearby is not a big deal. Now, for the electroencephalogram, all you have to do is have some amplifiers and some electrodes. Somebody put the electrodes on. It's really not very expensive. So the good news is the EEG is cheap. Whereas the MEG has all these coils that are in the liquid helium. You got to keep the liquid helium cold, and so it's a more complicated technology. So in general, relative to the EEG, the MEG is expensive. It's not as expensive as MRI and PET that we talked about last class, but it's more expensive than EEG. And there you have sort of the relative advantages and disadvantages of the two methods. Both of them have great temporal resolution. You can measure things at the time scales of milliseconds. Both of them have kind of bad spatial resolution, not nearly like PET and MRI. But most people use EEG. It's cheap, easy to use, well understood. There are people who claim that these advantages, especially this no effect from the skull, make MEG a much better choice. So you'll see people who are very strong proponents of the MEG. Right now, it looks like EEG is winning in the competition for what you use in the clinic. So that's a little bit about measuring magnetic fields. Next class, we're going to do the opposite. Instead of measuring tiny magnetic fields, we're going to apply giant magnetic fields. They're changing with time, and we're going to induce, by Faraday's law, induce currents in the brain. And you're going to see how that type of magnetic stimulation works. I will see you all on Monday. If you didn't hand in your homework, hand it in now.